As it turns out, calculus, and in particular the derivative, can be very useful in determining the behavior of a function. So for example, let's suppose we have f of x on some closed interval a, b. And I just did a generic sketch here of a nice continuous function. And let's just take note of some things. Think about this curve here, between a and x1. One of the first things you notice is that this curve is increasing. In other words, as we move from left to right, as x's get larger and larger, the function value gets larger and larger. Well, of course, this function is increasing. But notice what that would look like in terms of the derivative. In other words, what would the derivative be like here? Well, remember the derivative it gives us slopes of tangents at points on the curve. So let's just look at a tangent here. I'll just draw a nice tangent. Okay, there it goes. Now, you notice that this is just a tangent that I drew from on this interval a to x1. And notice that its slope is positive. In other words, the derivative for this tangent would be positive. And there's nothing special about the tangent I drew here. If I drew tangents anywhere from a to x1, they would all have positive slopes. So, in other words, the derivative here is greater than 0. That's one of the things we take note of here. So, that positive derivative would seem to indicate that we have an increasing function. Now, we could go the same way, to argue the same way over here. Notice from x1 to x2. See, from x1 to x2. Well, this function is decreasing there. And notice I drew a tangent here. And that tangent, like any tangent I draw in this interval from x1 to x2, is going to have a negative slope. So that would tell us that the derivative is negative here. Now so we start to see this connection that when the derivative is positive, that indicates that your graph is increasing. When it's negative, that indicates your graph is decreasing of your function, your graph of your function. Now over here, you notice once again, looks like we got positive slopes there. So f prime greater than 0, f prime less than 0 here, and then f prime greater than 0 for this interval here. Okay? So immediately we're thinking, with the derivative I can determine where a function is increasing and where it's decreasing. So that's one of the things. Now, what I want to focus on here, though, is this thing called extrema. In other words, I want to focus on if we have a closed interval like this, and we want to find the high points and the low points on the function. In other words, the maximum values and the minimum values. Can we use the derivative for that? Well, let's see. First of all, let's determine what we mean by maximum, what we mean by minimum, what we mean by extrema. Now, of course, if you look at this graph, you intuitively know where a maximum value is, where a minimum value is. That's obviously a maximum value here because, it's the biggest, it's the highest point on the graph. Here's a minimum value because in this little interval here, it's the lowest point on the graph. So what exactly do we mean by max or min? Well, let's consider this x sub 3. Now, there's obviously a max occurs there. There's a high point, a maximum value there. Well, what does that mean? Well, let's suppose I get a little interval about x sub 3. And let me go from smallest value to largest. Let's suppose that I have x sub a, x sub b, and then x sub 3 is here, x sub c, and x sub d. In other words, let's suppose that these are going from smallest to the largest. So x sub 3 is in there. See, so all of these are in this little interval. Let's suppose I can find such an interval such that f of x sub 3 is greater than or equal to any one of these. It's greater than or equal to f of x sub a. It's greater than or equal to any of them. F x sub c. You know, all of them. What if I can find such an interval? Well, that's what we're going to say is a maximum. Okay? So, you know, to be a little more rigorous than just eyeballing it, what we mean is it's the biggest, it has the largest function value of the neighborhood about it. Okay? Now, if we talk about the minimum, we do the same thing, except we say, like for example, x sub 4. We might say, well, it is the smallest, it's less than or equal to all those values, function values around it. Okay, so this one right here, it's less than or equal to all the function values in this small neighborhood about it. When that happens, we say, okay, that's a minimum. And in this case, it's just a local, right? It's not the, it might not be the, it's not on this interval from A to B, it's not the absolute smallest, right? This is a smaller value. But in its little neighborhood here, it's the smallest. So it's a local minimum. But that's what we mean. But you can just look at it and tell, right? Maximum, minimum, maximum, minimum, maximum, minimum. Now, where do these maxes and mins occur? Well, there's a max here, min here, max here, min here. Where do they occur? Think about what these all have in common. All these maxes and mins, all these extrema, what do they have in common? Well, notice the slopes of the tangents. If you think about the slopes of the tangents at all these maxes and mins, and if you try to draw the slope, if you try to draw a tangent there, they would be horizontal lines. See? Think about it. If you draw a tangent here, that's not horizontal. But if you draw it up here where this max is, that's horizontal. If you draw it down here where the min is, you get a horizontal. See? Every one of these places where if you draw a tangent, it's just a horizontal line. That means the slope is 0. Okay? In all of these places, that means that f prime of x is 0. Right? At all of these places, the derivative is 0. Okay? That's where the maxes or mins occur. So look, let's suppose, let's call these points, notice x1, x2, x3, and x4. x1, x2, x3, and x4. These are called critical numbers. These are called critical numbers, and the reason we call them critical numbers is because at each of these places, the derivative is equal to 0. Those are critical numbers. So you notice this. These maxes and mins occur at critical numbers. They occur when the derivative is equal to 0. Those are critical numbers. Now look what else? Maxes and mins can also occur at endpoints. So if you have f of x on a closed interval, you notice that a low point can also occur here at the endpoint, right, at A. There's a minimum, right? It's the lowest point of all the points around it, okay? And also over here, this is a max. It's the highest point around. In other words, the points get higher and higher and higher and higher until they get right here. And they don't get any higher than this. So look, here's what we have. We have a min, a min, a min, 3 mins there. And we have 3 maxes. Okay? Now, these are all local. In their small little neighborhood, they're either the biggest value or the smallest value. However, there is one here that is the absolute. It's the absolute biggest value on this curve. Now there's also an absolute min over here. This one right here is an absolute min. Right there, absolute min. So here's the thing. It's at the endpoints and at the critical numbers where you have maxes and mins occur. So let's take a look at this. Let's take a look at an example here. Let's suppose that we have f of x equals x cubed minus 12x on negative 3, 5. Let's suppose we have that. And we want to find the extrema. We want to find the maxes, the mins. We want to find the highest point and the lowest point on this graph, on this interval. The highest point and the lowest point. Now, here's what we know. We know that the high points and the low points occur in two places. They can occur at the endpoints and they can occur at the critical numbers. In other words, where the derivative is 0. So let's find where the derivative is 0. So here's what I do. First of all, I differentiate because I'm trying to find my critical numbers. So this is going to be 3x squared minus 12. And I set that equal to 0. So if I set that equal to 0, I have 3x squared equals 12. And that means that x squared equals 4. That means that x equals plus or minus 2. Yeah, so we have two critical values, two critical numbers, and then we have two endpoints. So let's do some testing here. Let's plug in to our function. Okay, and we want to plug into this function right here, x cubed minus 12x. That's what we want to do. Okay, x cubed minus 12x. And what I'm going to do is I'm going to plug in a negative 2, a positive 2, and then I'm going to plug in a negative 3 and a 5. So what I'm doing is I'm plugging in the critical numbers and the endpoints. And I'm just going to take note. I'm going to get a smallest number and I'm going to get a largest number. The largest will be the max, the smallest will be the min. So here we go. We've got negative 2 cubed minus 12 times negative 2. Okay, so let's see what that looks like. That's going to be negative 8 right there. A minus, so this is a plus 24. So that's going to be a 16. Okay, so I just take note of that. That's a 16. 24 minus 8. Okay, now let's look at the next one. We've got 2 cubed minus 12 times 2. And that's going to be 8 minus 24. And that's going to be a negative 16. Okay, so I just take note of that as well. Now let's put in the 3. I get negative 3 cubed minus 12 times negative 3. So let's see what that's going to be. That's going to be a negative 27 plus 36. And that is going to be, let's see, a positive 11. Positive 11. Well, actually, a positive 9, I'm sorry. Yeah, there we go, positive 9. Sorry about that. Okay, now we put in the 5, 5 cubed, minus 12 times 5. Okay, and let me see what we get here. We get 125 minus 60. And that is 65. Okay, so look what we've got here now. We've got a 16, a negative 16, a 9, and a 65. This is the max. That's the maximum value. The minimum value is right here. This is where the minimum value is. So the minimum occurs at x equals 2, and the max occurs at x equals 5. There, and we're done. Now let's look at another example. And to get ready to explore that example, let's just in general look at a curve like this. Let's suppose that we've got this function on AB, and it has a minimum here, you know, a minimum here, but it's got a maximum right here. Now, obviously here, the tangent, you know, it's got a horizontal tangent there. But notice up here, there's a sharp point there. And remember, derivatives shy away from sharp points. A function does not have a derivative at a sharp point like this. So we've got a situation here where f prime of x1 does not exist. Does not exist. Well, it turns out that we're going to add to what we're calling a critical number. A critical number is this. C is a critical number if this derivative equals 0 or if the derivative is undefined there. So in other words, if f prime of c equals 0 or if f prime of c doesn't exist, in either of those cases we'll call c a critical number. So when we're trying to find critical numbers, we set the derivative equal to 0 and solve it, and also we find out where the derivative is not defined. Okay, those are the two things. Now, so to illustrate that, I've got this example here. And if you look at the graph of this particular function, let me go ahead and do just a quick sketch. The graph is going to look, something like that. That's what the graph is going to look like. And we're going from 0 to 9. And you can see there's a sharp point right here. So let's go ahead and explore this. Now, first of all, if we're trying to find the extrema on here, we're trying to find the high point, the low point on this interval. First thing we do is we just differentiate. So I'm going to differentiate. I've got 2/3 x minus 1 to the 2/3 minus 1. That's going to be negative 1/3, isn't it? See? 2/3 minus 3/3, that's negative 1/3. Plus 2, the derivative of 2 is 0. So this is the entirety. This is the derivative. Now, I want to find my critical value. So let me write this way. I've got 2 over 3 x minus 1 to the 1/3. Now, if I set this equal to 0, there's nothing's going to make this 0. Normally, if we're trying to find, if we have a derivative and we want to find, okay, where is that derivative 0? We would set the numerator equal to 0 and solve it. But here you can see I've got 2 divided by this thing down here. There's nothing can make this 0. This can never be 0. We can't divide by 2 by anything and get 0. So we're not going to find any place where the derivative is equal to 0, but what we can do is we can find, well, where is the derivative undefined? So I'm going to do that by setting the denominator equal to 0. I'm just going to set this denominator equal to 0 and find, okay, for what value for x will the denominator be 0? And it's pretty clear that's just going to be x equals 1. At x equals 1, that's where that derivative is, the denominator is going to be 0. So this is a critical number. I didn't get a critical number from where the derivative is equal to 0 because the derivative is never equal to 0. However, it is undefined, and it's undefined whenever x equals 0. The derivative doesn't exist there. So now I've got my critical numbers, and what I've found is this right here. I found that point. So let's make our table and see if we can figure out where the absolute maximum and where the absolute minimum are. So I've got x, and then I'm going to plug that into x minus 1 to the 2/3 plus 2. And I'm going to plug in the endpoints, 0, 9, and then this critical number. So if I put in a 0, I've got negative 1 to the 2/3 plus 2. Well, that's going to be the cube root of negative 1 is negative 1, squared is 1, so this is going to be a 3. Okay, and you can see I found, this function value there. Now let's plug in the 9. See what I get. I get 9 minus 1 to the 2/3 plus 2. Well, that's going to be 8 to the 2/3 plus 2. Let's see here. The cube root of 8 is 2. Squared is 4. So this would be 6. And then I plug in a 1. Well, 1 minus 1, that's easy, plus 2. So that's just going to be 2. So it looks like what we have here is we have our minimum right here. And then it looks like we have our maximum here when x equals 9. So this is where our max occurs. So our min occurs when x equals 1, and our max occurs when x equals 9.